Hello, welcome to a video tutorial made by Robotix IIT Kharagpur for the Computer Vision event of Robotix 2014, Geo Aware. We hope that by the end of this tutorial, you'll have a good idea about how to go about attempting the problem statement of Geo Aware. So for your convenience, what we've done is we have divided this video into a few modules. So firstly, we'll be going over the problem statement and the various aspects on a large scale, the overview of the event, so to speak. Then we'll be discussing the various modules, and finally a little bit on how to combine that together to make the robot. The first module is the overview, and so in this module basically what we need to do is we need to take a look at the problem statement and the various components that we need to go about attempting this. The problem statement of Geo Aware is stated here. Create a vision guided robot which can use onboard video feed to navigate an environment based on an overhead image as a map. So, assuming of course that you have observed the arena, a sample arena for this image, which is given in our website under the rounds tab. This is our website, by the way, robotix.in, and this is obviously the event for Geo Aware. So this is something like what the arena might look like, a symbolic representation, of course. And what you will be given is, you'll be given this overhead map of this arena, which looks pretty much like this, a complete overhead view, perfect image. It won't be a real life image. And you'll have to process this map before your robot starts the run, and then the robot will begin the run, and as it moves across the arena, it has to basically locate itself using these landmarks, using the other information, and find out where it is and take the correct turn to reach the end. As mentioned in the rules, of course, once you go through them, this yellow patch refers to the starting zone, the brown patch refers to the ending zone, and these colored symbols are landmarks. They can only be squares, circles, and triangles of blue, green, and red color. So at most there can be 3 colors, 3 shapes, 9 different types of landmarks, and they'll be unique. This is all specified in the rules, so do go through that if you have any doubts. Okay, so now what are the various things that you might need to tackle this event? So yes, so if you have a look, these are the basic components that we'll need to discuss. Obviously, your robot will have to have some hardware. So what we're going to do is we're going to first discuss hardware separately as a separate module of a remote control robot. If you once I explain the abstraction, you'll understand why segregating this into a module in and of itself is a good approach. Then of course there'll be the computer vision aspect of it, which will be done by a webcam through your laptop or any other processing device. So for this particular event, as you can imagine, we'll need a computer vision for lane following to be able to follow those lanes or the corridors. We'll need to be able to detect shapes. We'll obviously have to be able on a general scale to process the map that was given. And we'll also discuss a couple of extra things which will help you tackle harder aspects of the event. So this is the brief overview of the event, and now we're going to go into individual modules. Alright, so after going through the overview, we're now going to look at the various subparts that we discussed, that we talked about there. And the first one, of course, is the hardware, which we will discuss by the abstraction of a remote controlled robot. Now this idea will become a little easier to understand once you have a look at this block diagram. So in this diagram, this is just a very simple block representation of a robot that might be able to solve this event. So of course, it would have to be an autonomous robot, so it would require things like a development board, a motor driver. We'll see what all of these mean in just a minute if you don't know them already. There'd be a power supply, of course, and it is a computer vision event after all, so there would have to be a camera on the robot, and this would be connected to a laptop, either wired or wireless, as the case may be. And any video feed that is taken will go from the camera to the laptop, be processed, and accordingly the laptop will send back instructions to this part to move in a particular direction, left, right, forward, backward. So right now what we're going to do is we are going to sort of ignore this laptop part for the time being and just focus on this part and sort of make like a hardware black box kind of design that will move, it can move in various directions depending on the instructions it receives. And then later on we'll see how these instructions are sent, and finally what leads to what instructions, as in what vision modules and observing what from the feed makes the laptop or your program give a certain instruction. That is something we'll discuss in the computer vision part. Okay, so now focusing on the hardware as such, as you can see, there are a couple of aspects to it. There's something called a development board, something called a motor driver. There's a sort of a wheels and a sort of body over here which we call the chassis, and there's a power supply. So I will not be discussing power supply in detail. It's very intuitive. You can either use batteries. All of these components will have provision for batteries, or you can use an adapter also by cutting out the jack, or you can even use a transformer rectifier circuit. So all of these are pretty simple to make. And of course, if you go to our autonomous tutorials and our AVR tutorials, autonomous particularly, you'll find whatever little you might need for making a power source. But as such is the simplest thing, so we won't be spending much time on it. Okay, so the next thing we need to do is we need our robot to move, right, according to instructions, and that's something known as a drive mechanism. A drive mechanism, and the one we use is the by far the most simple and the most intuitive, the most easy to use. It's a differential drive. Now, differential drive is very simple. Again, you can read up about it. This is under tutorial mechanical drive mechanisms, and the first thing is differential drive. So differential drive is very simple. As you can see here, there's a chassis, and there's at least two independent motors. A left motor, let me just zoom in so you can see this. Yeah, a left motor. This is the right motor, and this is the left motor. And each of these motors controls at least one wheel. They might control more independently. So independent turning of these two motors makes the robot move in a particular way. And how that happens again is very intuitive if you think about it. If both the motors move in the same direction, the robot will move in that direction. Let's assume that this is, again, if you look at this, yeah. So let's assume that this is forward. So the robots, both the wheels are rotating in this direction, as if moving towards this direction. The robot will move forward. Then if one of the wheels turns much more than the other, say for example in this case, then the robot will turn in the opposite direction. Again, this is easy to imagine. Imagine your left wheel moving slowly and your right wheel moving very fast. If you're at the center, you will tend to turn to the left. Another thing you can do is you can have the left wheel move backward like this way instead of forward, and that again will lead to something called a turn about the center. This is called a zero radius turn. While in this case it would turn while still moving forward. If the two wheels move in opposite directions with same speed or similar speed, then the robot will turn about the center. That's called a zero radius turn. Conversely, for when the left wheel moves faster, and again, if it wants to move backwards, it can move both of the wheels in the same direction, in the opposite direction to what you consider backward. So you have straight or backward if this is opposite. You can turn left while still moving forward, turn right while still moving forward, and this is called spinning in position or a zero radius turn. This is how a differential drive works. Again, this is very simple. You can go through this tutorial and try and implement it, or see some of our videos with regard to this. There's nothing much to go into here, and it's simple to implement also. Now, the next thing is how will these signals for the wheels to turn, how are they going to be sent to it? Okay, and for that we need to understand two concepts. There are two things there because they work together. One cannot really exist without the other in this case, and that is of a motor driver and a development board. Now, the development board contains what is called a microcontroller. As the name suggests, it's a small scale version of a let's say a computer. In a sense, it is a very small scale computer. It has the ability to communicate, to be programmed as you would program normally, and of course we assume you know programming since you're attempting this event. You can program it using certain languages. We'll see that in a minute. And it can be programmed to respond to particular actions, to particular events, just as a normal program can. In this case, the event will be certain instructions being sent to it from the laptop. Again, we'll see that a bit later. And based on these instructions, the microcontroller sends signals to the motor driver. Okay, sends signals to the motor driver, and the motor driver has something known as an IC or an integrated circuit, and that integrated circuit now gives like voltage to the motors, voltage difference across the motors, I should say, to make it turn in a particular direction. We'll have to define through our making this circuit and through our connections what kind of voltage from the IC for the motor driver leads to what kind of turning. That is something we can define, and that in turn powers the motors. Now you might be thinking, and it's very likely that you could, that why can't the development board, why can't the microcontroller directly power the motors? Well, here of course, as you can see, we'll be assuming, and in general you will assume, you will use motors that are of 12 volt. While these motor drivers and the development board specifically, it does not require that much. It can work on 5 volts. The components are made to work on 5 volts. So we need a motor driver which sort of is powered by 5 volt from the development board, but is also given a 12 volt from the power supply, and therefore the signals that are given to the motor driver are in terms of 5 volts, high or low, 5 or 0, whatever. But what the output it sends to the motors is of the form of 12 volt, and there's a lot of internal working that goes into that. We're not going to go into the details. Okay. So now of these components, firstly the development board, it has a microcontroller, which, as I mentioned, I mean, and as you can imagine, is kind of like a small computer. And I won't go into too many details because all of this you can find in great detail under our tutorials, AVR, and then AVR. Okay, let me just zoom out a bit. Sorry. Yeah, tutorials, AVR, and then AVR programming. You can find, yeah, just over here, AVR programming. You can find it out and have a read through this. There is sufficient detail to help you get it started, even burn your own first code. It's in C, other languages I'm sure you're common with, and there might be other workarounds for it also, but of course C is the commonly used one for AVR microcontrollers. That's one framework for designing microcontrollers. There is another one which we believe some of you might use. We'll just talk about that briefly just at the end. So once you have programmed the microcontroller to receive certain commands from the laptop, how we'll see in a minute, to receive certain commands, it then can give certain electrical signals or certain instructions, in a sense, to what is called the motor driver IC. Again, not too much detail here, since after all this is not the focus of this event. You can go through the motor driver IC under tutorial autonomous. There you see on the left motor driver IC, and you can have a look in detail how it works, how there's an H bridge, how different voltages across the motor driver causes the motor to turn in both directions, and that gives us the freedom we need for a differential drive. And there's a pin diagram. You'll need this while you're making your own circuit and connecting it. And we've even gone ahead and shown you how to solder it on a PCB. So everything is given here, everything is mentioned here in very great detail, including the code that needs to be burnt on your microcontroller to run a motor driver. So again, I won't be discussing this as such. If you haven't implemented this at some time already, have a look through this page and implement it. It's very simple to do. Okay. And the final aspect is that of communication. The laptop, based on the instructions that it infers after processing the camera feed, it'll generate certain instructions, and they need to be sent to the microcontroller. Now, this tutorial of serial communication is on our computer vision page, for that matter, because it's an integral part of every computer vision project, every computer vision robot. So if you have a look through this, you can get an idea of how to implement it. There isn't much theoretical detail. It's basically just simple implementation. The code you need to burn on your microcontroller, the code you need to use in your program in Visual Studio or any other IDE that you're using. Here we've assumed Visual Studio, where you'll write your computer vision code, your image processing code. There you'll need a code snippet there also, so as to be able to send instructions here. It won't just happen by itself. There are some files you need to download too for this purpose. Once you read this tutorial, you'll understand what those files are for. And again, we've also provided links to download these files, so you can download them. There's no problem about that. And once you burn the code of the microcontroller on the microcontroller and use this code snippet in your computer vision project whenever you make it, you should find that you're able to communicate from your IDE, your coding environment like Visual Studio or Code Blocks or MATLAB, whatever it is, with your microcontroller. And that's what you need, right? If you think about it, now what can happen is you can run your program on your IDE. It can take the visual feed, the information from the camera, process it, and then it can send instructions directly through the IDE to the microcontroller. And that essentially is how it's done. And the microcontroller is configured very simply. I should say that the character combination. We generally use WSD. If you just take a look at your keyboard right now, you'll see WSD is the common keyboard configuration for those of you who don't know. For racing games, sometimes where W means forward, A means left, S means down, back, D means right, and we can use something like Q or P for a brake. So this is the configuration we'll use. So if a character W is sent from the laptop to the microcontroller, now you can start imagining this, right? A character W is sent from the laptop to the microcontroller. Let's just go back to the block diagram. Yeah. And that character is then deciphered by your code, and accordingly the signals are sent, the electrical signals are sent to the motor driver, the voltage differences accordingly, and that is then amplified in a sense to 12 volt, put up to 12 volt, and accordingly it is sent to the two motors. So if W would mean that both of these motors would have a high potential difference of 12 across them in the same direction, whatever direction we've defined as forward, and the robot can then move forward until some other key is sent or something else happens. Okay, so I think with that we have a basic idea about how to make a remote control robot. You see why it's called a remote control robot now. You can, using your laptop, and especially if you have wireless communication, you can sit somewhere and pressing WSD, you can make your robot move around. So that's pretty much it for this module of hardware. Once again, if you have any particular issues, you can go through the individual tutorials for drive mechanisms, for AVR programming, for motor driver, and for serial communication. And finally, there is one more thing. There is a new paradigm or a new mechanism for autonomous microcontroller programming, and that's something known as Arduino. We also have tutorials for implementing whatever we need for computer vision events through Arduino on our website. And it's Arduino is more commonly used nowadays. It's considered to be in a sense simpler and more easy to use than AVR is, albeit more expensive. And if that's what you're using, or if that's what you intend to use, you can always go ahead and check out our tutorials for the same. Okay, so with that we come to the end of the hardware module. Now that we have discussed the hardware, the next thing we need to do is begin with the computer vision part of it. So as you can imagine, if you think about the event, the robot will be moving inside the arena. The video feed will be taken from the onboard camera. That will be processed by the laptop, and necessary instructions will be sent to the robot, which we've seen now how it can follow that and turn accordingly. So if you think about the event, the first thing that you need to do is to take the overhead map and process it. But we are going to take a reverse approach to this. We're going to first discuss the modules relating to the onboard camera, the onboard image processing for navigating the corridors. And then we're going to discuss the map processing, because once we know what kind of information we need from this onboard traversal, then we can modify our approach to processing the map accordingly. So the first thing that we need to discuss for that is, of course, following a lane, or basically the corridors of the arena, and that is the lane following module. So just right at the start, let me state that this is extensively covered under lane following. If you go to a tutorial and then go to computer vision with OpenCV, you'll find lane following is there. So I'll just take you to tutorials here, and then computer vision with OpenCV. You'll find that lane following is there. It's discussed in some detail as to how it's done, the method and whatsoever. We'll go over it very briefly here, but I won't go into too much detail as I won't with any of these modules, because all of these are mentioned. But the basic idea involves taking a view like this. Okay, taking a view like this, which presumably is what your robot will start off with. I'll just move back. Okay, this is a yellow patch, and this is the view of the corridor. Okay. Again, you can see how this is in sync. If you go to the tab for the arenas, where the arenas are mentioned, you'll see in rounds, you'll see how this is, for example, this is a different arena obviously than the one we just showed you, but essentially that's the idea. So you can then traverse the arenas accordingly. So what we need to do is we need to get rid, right now we're only focusing on following this lane. We're not worried about what lies at the end. We will be worried about that once we get very close. Now we're not worried about that. Okay. So alright, so basically the idea is to focus on this view and see what information we can glean about turning. Now if you have a look, let's say in this case it's somewhere parallelly between these two lanes, between these two lines I should say, and we need to be able to reduce all of this irrelevant information, at least irrelevant to lane following, and focus only on these lines. Because as you can see, once it turns, the nature of these lines changes. So this information, while the end of the corridor and all remains same, so it's this changing information that could probably tell us which way we need to go. I will just show you what the lines look like when removed. So this is what it looked like. So to do this, we just need to perform something called canny edge detection, for which there is a function implemented. Have a look at our general computer vision tutorials. Again, we hope you've gone through all of those already. Otherwise, it'll be difficult for you to follow exactly what's going on here. So we need to exclude the majority of the upper portion. We're not worried about the horizon and beyond right now. We're worried about this lower portion. And based on, and again, if you can try to visualize this, based on the relative angles of these two lines, based on the relative slopes of these two lines, we can make some decision about which way to turn, because that's what's changing between different runs. If you can visualize that. Okay. So now, so we need to be able to identify lines in the image and obtain their slopes. Okay. Again, this topic, before I discuss it in briefly, is also discussed in shape detection under computer vision with OpenCV. The reason being that this topic is, this concept that we'll discuss right now is widely used for shapes. Can be adapted for shapes besides being the concept used for obtaining lines. Okay, it's called Huff transform. Now, the basic idea behind Huff transform is basically to convert an image in the XY plane, which is what your 2D images are, pixels with as a 2D array of pixels, images in the XY plane, to something in another plane. Okay, and the transformation in this new plane will give us information about the old plane. So for the case of a line, let's just go see that. The case of a line, what we need to do is we represent a line in polar form. Okay, we represent a line in polar form where rho is the distance, the perpendicular distance from the origin, and theta is the slope. Because this lets us, if we can represent this, we can get theta directly, and that's easy to work with, that's easy to deal with. Again, for more details, please read the literature on this. It's very interesting, and this is generally a very interesting concept. But essentially what we do is we convert, using the equation rho cos theta plus, x cos theta plus y sin theta equal to rho. We know that this represents a line in the xy plane. But now what we do is we consider rho and theta as the variables. Rho and theta as the plane variables, not x and y. We can take x and y as a constant, for example. Then we'll see that there are infinite points or many points of rho theta that satisfy a given x and y. So, and since that theta is now in a sine and cos form, what we can do is we can say that a point in the xy plane, a particular point x comma y in the xy plane, by virtue of this equation rho cos x cos theta plus y sin theta equal to rho, a point in the xy plane refers to a curve, a sinusoidal curve in the rho theta plane. Just take a second to think about this again. Write the equation down if you have to. I'm not writing it here. Write the equation down. Rho x cos theta plus y sin theta is equal to rho. And now if you think about it, if you put a particular x and a particular y, there can be lots of values of rho theta, and this forms a curve in the rho theta plane, not a line in the rho theta plane, because it's sine and cos after all. So after all, it forms a curve. Okay, we also know that every line, in our original image, I'd say for this one, one sec, just run this, every line will have plenty of points on it with the same, let's say, similar rho and theta, right? This line has a lot of points with rho and theta in it. Okay, of course this is the ideal case. You might have a lot of noise here, which is why we need such elaborate measures to exclude simple bits and pieces of noise from getting in. So we'll need a kind of threshold that a line must have so many pixels. A line must have so many pixels with similar rho and theta to be able to be called a line. Okay, and if you've understood this, and if you haven't, please read it, but if you've understood this, then the algorithm becomes very simple, because then it becomes something like this. This is the algorithm for Huff transform. We will try to find out local maxima of rho and theta by getting all possible rho theta values for a given x and y. Okay, this is going to be a mouthful, so I'll just repeat this again. Let's say you're traversing, and I'll do this in another step here. You're traversing this image, you come across a point x comma y, which you can obviously get in relation to the origin, which is the top left. You get a point x comma y that belongs to an edge. You need to find with some, not with certainty of course, but with some confidence if it belongs to a line. So you get all possible rho theta values for it, and you increment that in this accumulator. You increment that in this accumulator and find out local maxima of rho comma theta, and those will give you the lines. Okay, it's that simple. Okay, just need to find local maxima, those will give you the lines. And you can assume bit, of course, that you have two major lines here. Once you get the two major lines, you get their slopes, see their sum, and make your robot move accordingly. And the algorithm can be simple. It can be that as long as the sum of lines is almost zero, keep moving forward. until you reach the end. That's a different state we'll come to in a minute. Or if it's not, then turn in a particular direction until it becomes so that the two lines, the sum of the slopes of the two lines is near zero. And if you keep doing this, you'll be able to follow the lay. We'll have a small video demonstration at the very end of this video for this very same thing. Okay, so that is that for this module. Right. So now that we've discussed lane following, the next module we're going to talk about is shape detection. It's a fairly simple one. It's small and it's simple to implement, and it can be black box to a great extent. There are not a lot of specific tunings that you need to do for this module. Now let's just have a look as to where we're going to need shape detection for Geo Aware. So we are going to need shape detection in two ways. One is when we have the map. From the top, we'll be observing the map and we'll be finding out where the various landmarks are, and we need to understand their shapes. And the second need is during the actual run in the arena. We'll be, as our robot traverses the arena, the corridors, it will come across symbols at the end of a corridor, and it's going to have to process it. Now, as you can imagine, in the real arena, it won't be as perfect. There's going to be much more noise. There's going to be more distortion. But we are going to discuss a couple of general concepts here, which with sufficient tuning and tuning and certain modifications, you can easily use it for the various requirements, for the different kinds of requirements you'll need. So to do that, what we're going to do is we're going to look at a simpler way of shape, since the color as such is not important here, and since the solid, let's say the inside is not so important, we're going to reduce this to something that can be more easily processed, and then you're going to consider it. So this is how you're going to consider it, in the form of an edge. Okay. Now, as you can realize, coming to this form will also be very easy. You do color detection for that color of whatever shape you're considering. Then you just run canny edge detection. You consider a region of interest of the image. You just consider a region around the blob that you're considering. Notice that at this point you should have seen our tutorials on blob detection, edge detection, and everything else needed. So again, I'm reminding you to go through all of those tutorials. That will help you understand. Now, so this is one example, this is another, and we'll also have a hexagon. I've not mentioned that here, but it'll be there for the final round. So the concepts we discuss can be extended to these cases. When you know it's going to be one of these cases, that's again another assurance you can have. It will be one of these shapes and nothing else. Okay. So there are multiple methods. The simplest one we feel is, not the simplest, yeah, in a sense the simplest, but also slightly risky, is to just count the number of corners it has. Alright, so for this, as you can imagine, this would have 3 corners, this would have 4, this would have none. You could do your tuning in the arena, see how many you're getting, try and look for that. So you can use something called CV find contours. You'll find the description for that in the document accompanies this video. CV find contours under shape detection. There's a detailed example there, as well as code as to how you can use that by counting the number of vertices of the contours. So for example, here there'd be 4 vertices, 1, 2, 3, if you just follow the pointer, and 4. Here there'd be 3 vertices, here there'd be none. So something like that. That is one way you can do it. Another way you can use is also Huff transform for shapes. So that would require concepts similar to the line transform that we discussed, where the difference is that in this case, as you would process this image, you just traverse it, you look for the white pixels which belong to an edge, suppose, and then suppose you can also compute the centroid of every blob, right? That's just simple method for computing the coordinates of the centroid. And having computed the centroid, you can look at the patterns of distances of the various edge pixels from this centroid. That's also something. You can compare the minimum and maximum distances, because again, the triangle you can assume will be almost equilateral. It's a regular assumption you can make. This is going to be a regular square, this is going to be a regular circle. So comparing the minimum and maximum distances, you can also get an idea of what shape it is. So there are actually numerous ways to do this. You can also plot the frequency of distances, of certain distances appearing, and then somehow manage that, because you can see the pattern, right? So if this is the centroid, this is a minimum distance, this is the maximum distance from the vertex, and there's a certain kind of variation here, then there's again a variation here, and so on, and there are 6 variations here, while for a square there'd be 8 such variations, 1, 2, 3, 4, 5, 6, 7, 8. So that's another way. So there are actually multiple methods. You can look this up online also. You can use trivial methods also. Like, I mean, there's actually a lot of freedom that you can use. Assuming you can assume ideal cases and use trivial methods also. So this is not really something to worry so much about. You could look it up. You can look in. We even have a description of shape detection here. It mostly talks about Huff transform. This is under computer vision with OpenCV. Computer vision with OpenCV. So it mostly discusses Huff transform in general, but it also touches upon how that can be extended to shapes. And finally, you can use OpenCV implemented functions also. You can match images, you can match templates. There's something called template matching, there's something called image matching. So there's a lot that OpenCV gives you. So again, this is not something that you would need to worry about. Okay, and if you have any specific questions, please feel free to ask us. But for now, I mean, this is it for this module. Thank you. Right, so now that we've discussed both lane following and shape detection, that essentially covers whatever we'll need for the onboard part of it. Although shape detection, you'll see in a minute how it can also be used here. But whatever we need for the onboard part has been covered pretty much in those two modules. And right towards the end of this entire video, we'll just go over the overview how to link those two. But right now we assume that the whole part of traversing in the onboard environment has been taken care of. Although now you're going to see why we wanted to take this reverse approach, why you wanted to do that part first. Because now if you think about it, now we know what kind of information we need from the map. We need, for every symbol, for every landmark, we need to know, we need to be able to locate ourselves in the image using that landmark. And this will be particularly important for a T-junction. Because if you think about it, I'll just show this here. Yeah. If you think about it, when you reach a T-junction like this, you won't know which way to turn, right? So you'll have gone through the arena as normal, and then when you come taking a right turn here, then then a right turn here, then a left turn here, then a left turn here. But suppose for this T junction, you won't know exactly which way to turn if you only use onboard processing. So that's when it becomes important to look at this map from above, process it, and find out which way we need to go. Okay. So how this map can be used, there are actually a number of ways you can use this map as information. We are going to be showing you one method. You can use that, you can adapt that, you can use a different method if you want. That's completely up to you. But so the method we are going to show you is, let's just have a look at the image. Yeah, the method we are going to show is basically trying to map a kind of sequence of moves. Okay. So if I know, this is a different map from the one I just showed you, but anyway, it gives you the same basic idea. If I know I'm starting here, which I know I'm ending here, and I know this, and I know for round 1 and 2 at least. Round 3, you'll see we'll have discussed later. So I start here, then I go ahead, I have this green circle over here. Now the thing is, even if this green circle wasn't there, if you just think about it for a second, you could have turned anyway. I mean, if you think about what this actually looks like, there'll be a corridor at the end of which there's just a right turn. Using only lane following, you could have turned in any case, right? And the same goes for here. But where the landmarks become important is in the case of a U-turn. So you try to localize yourself. They become particularly important in round 3 when you will not know where you're starting from, but we'll leave that for now. But they're even important here. So if so you know that you've gone past the green circle, red triangle. How we get this information we'll see in a second. You've gone past this, gone past the red circle, and then you've come to this T junction. And if you know by processing this map initially that you have to take a right, then you'll take a right. You won't have to guess. You might take a left, you might make a mistake. And so basically that's what we need. So when we have this image, we want to be able to map a sequence of turns so that particularly for the T junction, we know which way to turn. Also in general, it's a good idea that we know the sequence of landmarks that we are seeing and that we are aware of this, so that if there's a mistake along any one step, suppose the robot makes a wrong turn or makes some kind of mistake somewhere, it can correct itself, and that's more robust. Okay. So what we'll be attempting to do is we will need for this a concept. I mean, it'll help us understand obviously something called a waypoint. Okay. A waypoint is something like for this particular case, a waypoint is something like points across the map which are of certain importance, certain interest to us. And again, here we can assume that between waypoints, let's say you can just travel straight. I mean, you can directly go from one waypoint to the next in a sequence of waypoints. Okay. So if you look at this map,
the first candidates you'd consider for waypoints obviously would be all the symbols, all the landmarks. They're all points of importance, points where you'll need to do something. And also, of course, the start and ending point. So from this 2D image, and here we're talking about 2D processing, image processing as such, and not onboard computer vision. If I can consider these landmark, these patches, by doing blob detection, color detection, I separate all of this. I will show you a demo of that in a couple of minutes. Then I know these are my various blobs. Then these can be my waypoints. Okay. And I also need to see which two waypoints are connected. So how we'll do that is, and at this point I would also like to remind you to keep referring to our document tutorial which accompanies this. There the exact code and the exact algorithm is mentioned. But what we basically want to do is we want to find out which of these waypoints are connected. By connected, what I mean is, I mean that the line joining the two waypoints, okay. And here by waypoints I mean the centroid of this blob. How to calculate a centroid? Again, you can check that out, how that's done. It's a very simple method. So having done my blob detection, I have all of my blobs, separate blobs, or the colored patches, and then I find out which two are connected to each other. Okay, this is connected to this is connected to this. Suppose I can find that out. And then I'll have some idea of the sequence of symbols, and how that sequence is laid out in the actual arena. Now I'll come up against a problem when I get to this T junction. Okay, so one way that we found to resolve it is this. We want to, the T junction will be such that the line joining, it to the previous, and the line joining it to the next waypoint, both of those lines will be continuous lines. By continuous lines I mean that they won't have any breakage, any black portion between them, so that and this is very easy. What you can do is, again, look at the documentation. You can use something called CV line iterator, where you join the 2 points. It will iterate over all of the pixels along a line, and if there are no black pixels or very few black pixels, then you know that okay, this is accessible from one waypoint to another, because you can directly go through white area, all of which is accessible. Okay, so that is one way we'll create waypoints of our own in front of the T junctions instead of just using the symbols. Okay. So now how we go about it? Suppose we can. So how do we create this? How do we know that this will be a waypoint? I mean, you can't tell just by image processing, like just by this image, you can't tell necessarily that this will be a waypoint, right? So how we do this? The method we've adopted is, we start with the starting point. We know what the starting point is. Then we find out which waypoint is connected to the starting point. There will only be one, because from the starting point you can only go in one direction. So that green circle will be attached to it. Okay. So we know this is the current sequence. Then, so the repetitive sequences at the end of each turn, we look for the remaining, which among the remaining waypoints are directly connected to the end of the current sequence. Right now the end of the current sequence is green circle. So it's yellow, green circle. So that's the current end of the sequence. So we see that the red triangle is connected as well as a yellow patch, but the yellow patch has already been considered in the sequence. So now we consider this. We can use a simple linked list or stack to implement this. We push this into the sequence. So after green circle comes red triangle, then comes blue square, then comes red circle, and now we'll find out that there is no new waypoint, no remaining waypoint that is directly connected to the red circle. If you think about it, the blue square is already connected, and there's nothing else among the remaining waypoints that are directly connected. So what we need to do now is consider each of the remaining waypoints. So just have a look at this and think about it for a second. Consider each of them. Okay, if you drop a line from this in the horizontal direction and the vertical direction, and you drop a line from this in the vertical direction and the horizontal direction, they'll have multiple intersection points. They'll have one intersection point here, and they'll have one intersection point here. Okay, from here, if I just follow the cursor, from here, if I go down to here, and here I drop a horizontal line. I'll explain how to do that in a minute. So this is one point and this is one point. So again, this is assuming simplistically that there are straight lines and there are straight paths and all of that. So what we can do is we have these 2 points, and then we just need to check that which of these 2 points is now directly connected to both of these waypoints. So this point is neither is it directly connected to this, nor is it directly connected to this, because there's black space between them. So this becomes our next waypoint. And when this happens, we can put that waypoint in the queue, and we can put the next waypoint also in the queue. because we know that is going to be the next, and then we just resume normally thereafter. Okay, so I hope this idea is clear to everyone. We begin with the start point, we find the next. So at any point we have a sequence which begins with the starting patch. Of the remaining unconnected waypoints, we find out which one is directly connected, we connect it. If there is no unconnected waypoint which is directly reachable from the current end of the sequence, then we use the current end and we use all the remaining waypoints, yet unconnected waypoints, and we try to see where a T-junction will be. Okay, it's a bit of a mouthful, but just if you read the documentation and watch this video a couple of times, you should be able to understand it. Also, if you see the code, you can also understand how it's implemented. All right, now what I'm going to do is I'm going to show you a quick demo as to how this is done. Okay, right, yeah, just run this. I'll just take a second. Right. So for doing this, we need two images. We need two intermediate images, and these are the intermediate images we need. We can get this by doing color and blob detection. Okay, this allows us to focus only on the blobs, get their color, get their shape, get their location, everything. And this allows us to focus on the accessible paths. So now we've got rid of everything but the white areas, the white paths. Now we can easily, use the coordinates. Suppose just we follow this pointer. I take the coordinate of this triangle from here. I take the coordinate of this square from here, and I can check if they're connected, and so on and so forth. This triangle here, the circle here, I can check that they're connected, and I can check which two waypoints are connected and not connected, and so on and so forth. So these two images are very important. Now you'll see what happens after I do this. I've done my processing and I get this. This is just a result of everything I just told you. I get this waypoint. I've just drawn a circle around it for your convenience. There's a waypoint here, there's a waypoint here, there's a waypoint here, and these lines join successive waypoints. And as you can see, there's a waypoint here as well. I'm drawing this to show you that I was able to generate this, and I can connect this, and that's pretty much it. And now if you need to know the turns at every waypoint, they're also very easy. Take a particular waypoint, say this one, okay. Take the previous waypoint, take the next waypoint. Find a relation between the coordinates. So obviously one of the previous, either the previous or the next will have the same y coordinate or similar y coordinate, and the other will have the similar x coordinate, and that's an assumption you can make. So so now if the previous waypoint is say below and the next waypoint is to the right, if you think about it, this will mean a right turn. Okay, if the previous waypoint is below and the next waypoint is to the left, suppose, then that would have meant a left turn. If the previous waypoint was to the left, like here, like previous waypoint was to the left and the next waypoint is to the top, that will mean a left turn. This way you'll get around quite a few cases, like based on the previous position of the waypoint and the next position of the waypoint. Based on this, you'll get a number of cases, and you can just code separately for each case. Consider each waypoint, consider the previous and the next ones, and based on that you can determine what turn you need to make at that waypoint. As I mentioned, that's not very important for these colored waypoints because you already know which turn you have to make, but they're very important, essential for the T-junction. That's why in general it's a good practice to just do it for all of them. What will happen then is, if it will help particularly in round 3 when you won't know exactly where you're beginning from, and you'll see that in more detail when we talk about hints for round 3. And that is pretty much it. And just to show you that I have that information, I don't know if you can see it, but hopefully you can. This shows, there's no font size in Visual Studio Printing, unfortunately. This shows straight from start. This shows right at green circle, right at red triangle, left at blue square, left at red circle, right at T-junction. This is just printing the various moves. It's just showing that we have all of that information I told you. We can access that. And now once you have this sequence, now when you do the onboard run, when you actually come across this, you can refer to the sequence, you can take the turn, you can just take the turn normally, that's also okay. But when you come across a T-junction, more importantly, you note what was the last landmark you saw and use that. Like here there's only one T-junction, right? But it might be a case where there's two T-junctions, suppose. And suppose it so happened that this here left was here both of the T-junctions require you to move right. But suppose one of them required you to move left, the other required you to move right. So when you reach a particular T-junction, the best way of knowing which way to move is remember what was the last landmark you saw just before that, and that will tell you where you are in the sequence. Okay. Again, for round 1 and 2, what you can do is you could just, instead of considering, during the onboard thing, instead of considering separately at each at each end of each corridor, what you should do, you could just blindly follow the sequence you generated from the map. If you think about it, take a right at the first corridor, take another right, and so on. But this is less robust, and it will be prone to errors if there's some problem along the way, and it's not so prone to readjustment. Also, you will not be able to notice tunnels by this. We'll discuss tunnels shortly in the next module. You won't be able to notice tunnels by this. So you can do this if you want, but it will give you problems in round 3 as well as with tunnels. So a better idea would be to do lane following, reach the end, do shape detection, compare that shape with what you've observed from the map, and then take your decision accordingly. Alright, so with that we come to the end of this map processing module. Thank you.
Right, so we've discussed most of the modules you'll need for Geo Aware. We'll talk about combining them just a bit later. But before we do that, I'm going to give you a few hints on the two more difficult aspects of the event. I'm sure if you've gone through the rules, you'll be aware of this. One is that the existence of tunnels in round 2 and 3. And also round 3 in general, it can have variable starting points, and it's going to have target zones also in addition to the ending zone, which you can visit for extra points, a lot of extra points. So in a run, it might be worth your while to visit that. So we're going to discuss two of these things. By discuss, of course, here I just mean I'm going to give you some hints, some brief ideas, because implementing this as well as integrating everything, that's the real charm of this event, and that's where the real your real abilities will lie. But just to give you a good idea, we'll just have a look at the tunnel and we'll see possibly how we can approach that. So here is a sample round 2 arena. As you can see from above, it doesn't really look like there's a tunnel anywhere, and it's difficult. I mean, there's no way of guessing where a tunnel might be. But if you look at the side angle, as you can see, there's a tunnel over here. If you just follow my cursor, you can see there's a tunnel over there, right? So yeah, so there's a tunnel over there. Let's take a closer look. This is the arena in SketchUp. So this is the overhead arena. And if I turn it like this, yeah, I can see a tunnel over here. So when I see it from the top, I won't be able to see it. But when my robot is going through and it takes a turn, it's going to see the tunnel, right? And as you can see, this is, I mean, normally you would expect to see a T-junction here. I mean, assume following from the previous model, if you've done the sequence correctly. What would the sequence be, by the way? It'd be straight from the start, then right at a red circle, then left at a green, then right at the T-junction, then left at a green triangle, then left at a blue circle, and so on. But suppose when you took the right at the circle, you expected to see a T-junction from your original sequence, and instead you come across this. So this is one general hint, one idea you can think about. When you expect to see a T-junction, or when you expect to see a wall, I mean, that will be different from if the path is continuing, right? So here I would expect to see black, I'd expect to see the lane ending, but instead I see the lane going ahead. So when you expect to see something and instead you see a path or you see a lane, then chances are it's a tunnel, and chances are taking it are going to, taking the tunnel is going to help you. Okay, this is important. And this is where it's different from mapping out the sequence right from the start. Like for example, if I mapped out right from the start that I would first take a right, then I take another right, then I take a left, then I take another left, and so on and so on, I probably wouldn't have even seen this, I wouldn't even have bothered. But if you make your program so that at the end, after every turn, make your program more generic, more robust. After every turn, it goes and it reassesses the situation. If the situation is expected, if it's expected that there's a corridor at the end of which there's a turn, then it does that. But if it's something unexpected, then it works accordingly. So that could be one way, and perhaps you could keep a check that if you expect to see a wall and instead you see a path going forward, then what you can then do is see just after the turn. I mean, assuming you've done modules 2 and 3 correctly, just after the turn you're here, right? Let me just turn this around. Yeah, just after the turn you're here. You're in this. If you just follow the hand, you're in this part, and you also know that in this image now, if you see a path in front of you, you can understand you're in a tunnel. So let's say you move to a different state. We're trying to estimate where the tunnel will lead. What you can then do is, if you know you're pointing this way, and you can know this because you know you've turned right, you can just drop a ray, I mean in the image, from this waypoint of the T-junction, you can drop a ray, say something like this,
and until you hit another white patch. Okay, so you can just traverse this line until you reach your first this you'll do this on the actual image, say this one, this image. So you can drop a ray maybe going along this black patch until you reach the next white patch, the middle of the next white patch. Just do your programming skills here, and you can find out where that is, and if that is, if that's further ahead in the path, which you can again also check. You can check which of the landmarks are directly connected, which of the waypoints rather are directly connected. You'll probably get that this waypoint and this waypoint are connected to the new point that you have. Then you'll know that okay, this might be a better place to end up in, and you can take this road, and again you'll know that you're pointing in this direction in the right, and you'll know that your next waypoint is here. So again you can figure out that you have to take a left turn here and then take a left turn. You'll save all the time that's needed to do this. This might particularly be important in round 3 also, we'll see that in a minute, but even here it's conceivable how it can help, right? So just an overview, just to summarize again, process the map normally as you would. You can't know where a tunnel is, so don't even bother trying. But during the onboard run, at every waypoint, check again. Don't just rely blindly on your map. I mean, this is what humans do, right? This is where the problem statement comes alive. You don't just check blindly, just follow the map. So check where you are in the actual onboard feed. See if that's what you expect, and if not, then accordingly make a decision. Okay, so that is that. And finally, the third thing we're going to discuss is, the last thing we're going to discuss in terms of hints is round 3. Now, what's special about round 3? So what I'm going to do here is I'm going to just open one of the sample images of round 3. One sec. Yeah, so this is a sample image of round 3. Okay. Don't let it perturb you. I mean, we'll discuss this and how we can manage this. But as you can see, this conforms with what we expect from round 3. There's a single ending zone here. There are red hexagons, which are the target zones, which you can get for extra points. There are normal landmarks, red, green, blue, and there's no fixed starting point. Okay, there's no fixed starting point. So you must be wondering, okay, how do you go about this? I mean, this seems so weird. I mean, how are you going to manage this? The principles, however, are still the same that you applied in round 1 and round 2. You're going to do the same thing. Okay, I mean, this is one possible way. You're going to find out all the blobs. Okay, you're going to find out which are connected. You're going to generate waypoints where none exist. So for example, I'll have a waypoint over here, I'll have a waypoint over here, I'll have a waypoint over here, and you're going to basically generate waypoints wherever they are there to be generated. So whenever two landmarks are not connected, so you're going to run this connection that we discussed in the previous thing for all pairs of landmarks and find out which of them do lead to waypoints, and if they're not existing waypoints, then you can generate them that way. So this way so it's going to be slightly different from the previous round where you had a starting point, so you just follow that in order. Here you're going to have to first consider all pairs of landmarks and generate the waypoints if they exist and if they're not there currently. So for example, this blue square and this red hexagon, their intersection waypoint is a green triangle, okay, which already exists, so you don't need to add that. But this red hexagon and this red circle, their intersection point is this waypoint, which doesn't currently exist, so you can add that to your database. Okay, so once you have all of these waypoints and you have all of the connections, now it's actually pretty simple because you have the connectivity, you know where you're going to end up, that's this brown square. You can just work back from the brown square and you can get a route from every waypoint to every other waypoint. So you can get lots of possible routes. Okay, now the thing is, you don't know which start point you're going to have, right? So what you can do is something like this, something of this sort. You can just make your code for round 3 so that when it starts, it just moves forward. Okay, I mean, obviously we're not going to put you in a position where you'll start off immediately with a wall in front of you. We're going to put you in a position where you can start. So maybe we could put you here. I mean, for this map, this won't be your actual map, but for this map, we could start you off here, pointing in this direction or this direction. We could start you off here, pointing in this direction. We could start you off here, or we could start you off here. And you'd obviously be pointing towards something. So just move straight until you reach the first wall and find out which landmark is in front of you. Okay, find out which landmark is in front of you, and that will tell you where you are. Okay, this will work for all cases except if the first landmark you come across is a red hexagon, but don't worry, we won't put you in such a situation. We'll take care to ensure that you're able to identify your position in the map once you see the first landmark. Okay, Now once you've done that, once you've observed the first landmark, the rest is actually not that difficult. Now you look at the information you had, all the connectivities, all the possible paths that you found out, then see where you are in relation to that. For example, if I had a path that had me turning left at this green circle and then all of this, and instead I start from here, so I come to this green circle and I see that I have to turn right. This is where it's important to keep correlating your position. So I come to this point, I see from here, from here I come here, and I see that I have to turn right. But in my original path, I know that I had to turn left. So that means I'm approaching from the opposite side. That means in my original map processing, I assumed I would approach from this side, but instead I'm approaching from this side. So I'll just do a U-turn. You can make a separate case in your code. I'll just do a U-turn and then follow the path as I would have otherwise. So here U-turns will also become important, particularly when you're visiting these red hexagons, especially ones at dead ends. So you'll also have to understand how and when you need to use U-turns. And finally, your goal should be to reach the end zone. If you're not worried about the hexagons, it becomes easier. You can easily just, instead of working forward from the starting zone as you do, you can work backward from the ending zone till you reach whatever is the first landmark you've seen in your run. So you'll have to process the map during the run also. Basically, come across a landmark, then find out, work backwards from the ending point to your landmark. So say I come across this one, so then I'll get this waypoint, I'll get this waypoint, this one, and so on and so forth, and then work backwards till you find out the way, and then just retrace that path. You can do that directly, and you'll visit you'll reach the end point. But of course, the credit lies in if you actually can visit the bonus zones also on the way and get more points, because if it comes down to it, a team which visits that is probably more likely to win, given that time won't be as important a factor as these bonus points will. Because time only becomes a factor if you have the same number of points, but if you have more points, you will win. I mean, as long as you're within the time limit. So this is just a general idea like I gave. There can be other ways to do it, there can be other methods also, but this is perhaps one base on which you can work. And yeah, that's pretty much it for all the various modules and components that you need for Geo Aware. After this, we'll just quickly go over a summary, and then I'll just show you a demonstration of one of the modules on video. Thank you. Alright, so with that we come full circle, we come all the way back to the beginning. So I'll just very quickly summarize whatever we've discussed till this point, and hopefully that will help put all of this together in perspective. So we first had a look at the problem statement, and we discussed the various components that you might need. In hardware, we talked about a remote control robot, where we talked about how to make a differential drive, how to communicate, how to burn code onto a microcontroller, and basically create a module that turns left, right, moves forward, depending on instructions that are sent to it from the laptop. Then we talked about the computer vision modules. So we went backwards first. First, we talked about the onboard camera portion, the lane following, the lane following using line transform. Then we talked about the shapes that need to be detected using Huff transform as well as corners. We are going to need all of this when the robot does its onboard run. But how will it know where it is? How will it know which way to turn? That came up in map processing, where we saw that we take an image, and in the actual event, this is what's going to happen. You're going to be given an actual image. If you just look in our rules, it's mentioned there. You're going to be given an actual image that needs to be processed, and then your run can begin. So we'll give you the image, and after that you won't be able to do anything. It'll have to be done autonomously, which is why we'll be releasing some maps online for you to practice on before. So we'll release, we do map processing, and then you get the sequence of instructions that you need. Then we come around back to the actual onboard feed, the onboard processing. You'll implement whatever we discussed in these two modules as and when. So let's just have a look at the thing again. So when the robot starts, now that we know everything, okay, so we get a lane like this, we move forward. Right now we're not bothered about the symbol. Then we see the red, and then we go back to our map, and we remember that a red meant turn right. Then we turn right, and then, okay, let's not worry about the tunnel right now. Let's just assume, okay, suppose this was black, but even if there is, we can go forward, or we can take a right, in which case we're going to go here. And so we need to create some kind of state. For example, in this situation, we're looking for the lane,
We're not worried about the symbols. We move sufficiently ahead, maybe to this point, and now we stop looking for a lane. We just look on the symbol, and then we can make a turn until we reach the rest of the arena. And that's pretty much it. Just go to the top. Yeah, and that's pretty much it. Just remember, you'll be given time here during the event. There'll be a practice arena where you can take your time. There'll be practice images, maps we'll have for you to practice on, where you can take your time and do your thresholding, test that your code is running. But during the actual run, we won't give you much time. You'll be given the image and your code. So once again, just build your code so that the first portion does the map processing. It takes an image as an input. The first portion does the map processing, then it waits a bit, and then the onboard run does not start until map processing is over. That way, when we place your robot at the arena, once the code begins, it won't start immediately. Once the map is processed, then the onboard feed is reached, and then instructions are sent. So yeah, I think that pretty much covers it. We'll be having a detailed text tutorial DIY that accompanies this. It has pretty much whatever we discussed, along with some extra things that are better written than said, because otherwise there'd be too much information. So it basically contains a documentation of all whatever we discussed, and whatever code modules we use. There'll be one for lane following as well as one for the map processing, the one that I discussed. Use that at your own discretion, but do remember that just using these alone will not be enough. The rest depends on you and how you utilize that. But yeah, in general, I hope that this was useful and that it'll put you in a better position to attempt the event. So thank you for that. Now we're going to just show you a video of the lane following module being demonstrated, so you can see that that actually works, and this was done using the very same computer vision module that we discussed. Thank you.